Good morning. We're starting our lecture on October 9th. Time is clicking on by. We will be talking about Exam 1 today. And you can actually see in the website here, I posted last night when I was working on grading and reviewing materials and putting together set number 4, I also said, yep, I better do the Exam 1 announcement, and that is embedded inside of a little note is embedded inside of homework set number 4, and then while I was at it, I had to go ahead and post solutions up to 2 old exams. So those are now here in the website too. If you look under the exam solutions section, I've got 2019 and 2022 exams. I went for 2021, but I could not get the PDF file small enough. With the WordPress website, I have to stay under 8 megs per file, and even though I was deleting material to try to get the PDF to shrink down, it wasn't working easily. So you've got 19 and 22, which are still very representative, and we may go over those today, depending upon what the decision would be as to when the exam is going to be. But if we move up here and go look inside the problem set number 4, I put a note inside of there too, so if people don't do anything but just go ahead and look at set number 4, which I've already got opened up here, you can see that I do talk about the exam. So let me just go through my plan, and then hopefully the rest of you will be here a little bit later in the morning, and we'll make the decision what we're going to do. So I've got the due date of this set, number 4, shifted out 1 week, and it's because I know the exam is going to come in there. And this set number 4 is on Chapter 4, which is sampling theory, multi-rate, random processes. There's a lot of things thrown into Chapter 4. So I'm looking at dates of October 16th or 23rd, and make sure I was not too far gone last night. There, I look on the calendar that's popped up here. You can see those are the next 2 Wednesdays. And then I've got the set that I just gave you due on November 1st is the plan right now. If things move along more quickly, but this is, set number 4 is for the entire Chapter 4 material, except a little bit on random processes will show up in the following assignment. So if we decide that we're going to go with the 16th, because this exam will be over chapters 2 and 3 of the text and notes, which we're wrapping up today, then I'm prepared to go through the review today. You have your crib sheet, and then I have the old exams already on the website. They're under password. You can do the same thing I'll do today. I will go through them. If we decide to delay it off to the 23rd, then I won't do the review of looking at the old exams until next Wednesday. The exam format, though, is I generally use the second half of the period. I use slightly more than 1 class session. So generally I stop at around 9 o'clock or so and take a break, and then we come back and start the exam. I don't want to give you, almost 3 hours to work an exam. It's not a good use of the time. But that's the format of the way the exam will work. And they're all 5 pages. The ones that I have as samples on the website are absolutely representative at this stage in my post-career, since I'm doing this, after I've officially left. I'm not in the business of generating lots of new problems. I have a huge catalog of problems that I've used over the years. I will reorganize the exam and pull problems that are in the same vein as the problems that are on the samples. And the samples are good, I think, to study from. The old homeworks, of course, are good too. The exam problems, I think, give you the absolute flavor of what I'll be looking for. I don't want to make it miserable for me to grade either. So right now we won't discuss the merits of 16 versus 23. Instead, I just want to get back into where we are in Chapter 3, and hopefully we'll be starting Chapter 4 at the end today, but it depends on what we decide to do. Hopefully those in attendance today, of which less than half are here right now, will be able to make that decision. And one student decided to depart yesterday or the day before. He said he's just got too much to do, so that doesn't mean he won't be in class today, because I think he might be the type of person that might still come. I don't know. That's something TBD, of course, too. I do have my solutions for set number 3 with me, and my progress on grading set number 2 has been very, very good. I'm down to the last paper. I just had some issues to deal with that didn't get me through that, but I will get that back to you. You'll see the histogram pushed out on that. I'll probably be working on that right after I get this computer working on processing the video to get ready to push that up there. Because I'm doing this on YouTube, I'm getting a few new people that join my YouTube channel, so to speak, right? I'm not really keeping up with it. If you're a YouTube watcher, you know that you can write comments and respond with comments. I'm not really focusing on that. My son, who does this sort of posting for our church, he looks at all that stuff because that's kind of what he's into, but I'm just kind of keep my head down on stuff that I want to be working on. So we will be back over here in our notebook, and we'll mostly be today looking at inverse E transforms. But before we get there, we have to look at some more things in the notes. One of the things that I did last night, though, that might make you feel better, I mean, it wasn't a good thing, but it was a thing I could recover from. I decided to add another package into my virtual Python environment. Remember, that's what I've had you do, right? And I did not like what happened when I added that package, and it kind of messed things up for me, and I said, this is not good. But it was something I discovered in my work yesterday, and I decided I'll try it on one of my not work computers and just see if this added feature, it's called the language server for Python and Jupyter. And so what did I do? I followed my own instructions that's on that document that you followed to install. Down near the bottom it says how to delete a virtual environment. Did anybody notice that? It of course works. You can blow that virtual environment away and then just rebuild it again, and I'm back to where I was. I maybe had a couple extra packages I put in that environment, but that's kind of the risk you have, but it's gone, and then I restored it. It takes a bit of time to do that. Not really too bad, though. My biggest frustration with doing that at my house is our microwave oven jams our Wi-Fi pretty badly. And I won't go into the details. I brought home a spectrum analyzer, field fox that we have in the labs to try to figure out. It's definitely, I mean, it's fair game. It's legal. Whether the microwave's leaking too much, I don't know. I think more likely it's that everybody else in my neighborhood has picked a different Wi-Fi center frequency and left me with the one that's right on top of my microwave's frequency. I can't move to another one readily because of the proximity of the other neighbors. Does that make sense? Has anybody ever thought about that? There's only so many Wi-Fi bands out there, and I'm also been working on getting the other websites that were lost in the shutdown for the Com1 class and the Com1 lab. I have to have those up for next semester, even though I'm not teaching them. So there's a nice homework problem, or quiz I think it was, in Com1 that dealt with Wi-Fi bands and the selection. This is in the 2.4 gigahertz band. So what we skipped over last week very briefly was just after we were studying various properties of the Z transform, the forward transform, especially the region of convergence. This is just a quick summary of things to remember about sequences. So if it's a finite duration signal, it's going to be if it's a causal sequence, remember right-sided sequence starts somewhere back over in here and goes off to the right. Strictly causal sequence is one that starts at n is equal to 0. It will guarantee to be the entire z-plane except z equals 0. And when you look at this, I want you to just think, in the z-transform, there's going to be negative powers of z only in this transform, right? Which means you're going to have a singularity at z is equal to 0, because you have 1 over z squared, and so on. If it's anti-causal, so it's a special case of a left-sided where it runs to the left starting at n is equal to 0, then it will be the entire z-plane except for infinity, because there's positive powers of z due to this anti-causal sequence, and it will have a singularity at infinity. If it's two-sided, finite number of terms, you have both positive and negative powers of z, so you have to exclude both 0 and infinity. And very frequently in the homework problems, especially some of them you've already worked, and you will continue to use the z-transform the rest of the semester, if you have a region of convergence that excludes infinity, right away when you see that, you know that you've got some positive powers of z sitting out here, because that's the reason why you can't go out to infinity, right? Because you would be unbounded. So that's kind of a useful clue if you can't include infinity. So if it says ROC is greater than something but less than infinity, that less than infinity lets you know there's some terms to the left of n is equal to 0. If it's a finite duration sequence, then if it's causal, it's just going to be the exterior of the largest pole radius. If it's anti-causal, it's the interior of the smallest pole radius. And if it's two-sided, it will be the annular region that we've talked about. So now we're going to move into formally the inverse Z-transform. We looked at this briefly last week. We have the contour integral, and a few, probably decades ago, every graduate student in electrical engineering, when I was in school, undergraduates didn't even have a DSP course to teach because it was so relatively new that they were only offering it to the graduate level. And they probably, in that day, they would have assumed that people had taken complex variables from the math department, like I did eventually. It's sort of faded out in the DSP books. It's no longer in Oppenheim and Schaefer, but this is formally how you would go about getting the sequence back from the Z-transform. Of course, we know as electrical engineers, because we learned about Laplace transforms at a young age in our degree, that partial fraction expansion is the name of the game most of the time, and it's absolutely true here too. There are certain advantages, and I have all these theorems that I've left in the notes that can be useful, but as a practical matter, they're generally, overkill from what we're interested in. So we're mostly interested in partial fraction expansion. The so-called inspection method, which the book talks about, is just simply saying if I see this in the table of Z-transforms, that's by inspection that I know what the transform pair is. And power series is just for some transcendental functions that you might want to get after the terms through a power series expansion. So, like I said, the inspection method is really just looking at this table. And this is a short table, but it's adequate for our purposes in this class. It's missing really not much of anything. I mean, if I was to say I'm missing something, this transform pair right here is only shown for a right-sided causal sequence, but there should be another version of this guy right here for magnitude of Z less than the magnitude of A. So the complement to that, kind of like what sits right up above here. We will be using this one at one point, but we'll only be using it for k is equal to 2 in one of the example problems, and I think in the homework you use k is equal to 2 as well. But I'm going to talk about another older technique. Older, when I say older, it's what I first learned in the Laplace domain back in circuits. It's a technique for partial fraction expansions. So these others will be bumping into every now and then. This last one, we already proved this one. In general, though, I'll just say that when you're working a homework problem, you refer to this table, make it go as fast and efficient as possible. If you have to prove a new theorem or something, you have to do that because that's the nature of the problem. It says find the z transform of this. So you find it, and then you have a transform pair that you can use further down the road. In the exam, however, you will have this table in your cheat sheet that you'll bring into the exam, and you can go ahead and use it. If an exam problem says show that, you know, as in starting here without using a table, that's what I'll mean. That will be clear about the problem now. Okay, so the partial fraction method starts by wanting to do a partial fraction expansion, but the first step is proper rational. So we have to make it proper rational by making sure the highest negative power of z in the numerator is at least 1 less than in the denominator. So we'll be using this form right here, ratios of polynomials and negative powers of z, not positive powers of z. But when you're trying to identify poles and zeros where they're at, this is generally what you end up having to do to see that. The function that I have in Python z-plane figures that out automatically, right? You put in exactly from what I circled here in red into the function z-plane, and it works from the coefficients in that sense. So proper rational is just saying if m is greater than n, then we have to do some long division. The other statement I have here is it tells you how many poles at 0 or how many zeros at 0 you're going to have, and that's what this leftover business is here that this second form is really kind of alluding to. From that, you can more clearly identify where the poles and zeros sit, and if m is greater than n, then you're going to have a leftover positive power of z down below here, and that's going to give you a pole at 0, and if you have n greater than m, then you're going to have a leftover 0 at z is equal to 0. So that's these two bullets along the way. This is a fundamental concept, though. Always the total number of poles equals the total number of zeros. Now this means that at times you have to consider the fact that there may be a pole at infinity or a zero at infinity. And a way of thinking of a pole at infinity is just like what I was saying about the region of convergence. Why would the region of convergence not include infinity? That would say effectively there's a pole sitting out at infinity because you're going to hit a singularity when you go out there. And I'll try to sort of illuminate that as we go along, but that's a general rule, though, about balance between poles and zeros. And if you don't see them at not infinity, that's when you say, oh, there must be a pole at infinity or a zero at infinity. And in reality, if you take a finite duration, think of finite duration sequence and shifting it to the left, or right, and shifting it to the left, you're really rolling off either a zero at infinity or a pole at infinity, depending upon which direction you're moving it. I can show a sketch of that, too. In order to do our method, though, we have to assume that we have a proper rational function. So we have m less than n. That's for the partial fraction expansion. If m is greater than or equal to n, then we do a line division and factor out some negative powers of z from that line division, and then we're left with the proper rational right here that we can do the partial fraction expansion on. So the simple case is distinct poles, and that's the one that's treated first. So we have poles that are all individuals, not repeated. They look of this form. So the partial fraction expansion, again, assuming that we have a proper rational function, will break down into n coefficients, a sub k, for each of the distinct poles in the system. And this is what I talked about last time, that we will always expand using negative powers of z. If this was done using positive powers of z, then we'd have to have a z transform table that's set up to work with positive powers of z. And there are books out there that do that. What I said last week, and I'm going to say again, don't look in those books, because if you try to do a hybrid, you will get confused and you'll get the wrong answer. Just stay with the flow, and negative powers of z are just better, in my opinion. I mean, for doing the inverse z transform, because it relates to the reality of delay in system. A z to the minus 1, you think of as a one sample delay, and that's a causal thing. If we go the opposite direction, we're talking about being non-causal. So if we have a distinct pole, we have a formula in the blue box here at the top just saying what is the coefficient ak. We take our proper rational x of z, multiply it times that pole term whose coefficient we want to solve, and we set z to the minus 1 everywhere in that expression equal to dk to the minus 1. Now you might take exception to that, saying I can handle this. I recommend following these instructions. You know what dk is. It's sitting next to the z to the minus 1. So if it's 2, then you're going to substitute in 1/2 everywhere for z to the minus 1. If it happens to be 1/2 for dk, then you're going to substitute 2. Does that make sense? So why I'm saying to do this thing red circled is just don't try to think too quickly in your brain, because you will again make a mistake. You'll just plug in the inverse instead of what you're supposed to plug in. It happens though, and on an exam you're always working at Mach speed, right? And you're instructions on that exam sheet, Doctor? No, but you can add them to your crib sheet. I didn't tell you this at the start of class, but for the exam you're going to have that formula sheet, which is, I think, 3 pages. Is that right? Yeah. And I'm assuming everybody can print that on their own. I don't need to bring you a copy. And then you're going to have one 2-sided sheet of your own notes. So you can put things like that on that. And the notes idea is you're studying and you write down some things on a scribbly sheet and maybe put circles around it. And then when you're done studying it, you would go back and say, how do I want to clean this up and put this on the sheet for the exam. And I'll have you turn in that sheet when you turn in your exam, just so I can see what's on there. Not that I'm going to go after you for anything. It's just if you did a dumb mistake and I end up seeing that dumb thing on your sheet, I'll understand maybe why you did something wrong. But I just like to have it, and then I'll give it back to you. And these crib sheets or study sheets are useful even for the final exam. Exam 2 will be take-home. Exam 3, or the final exam, will be here in class. But having those sheets can be a lot more beneficial than having all the notes. The final exam will be open book, open notes, but all that stuff sometimes can be overwhelming. My strategy would be, I'll have some study sheets that I wrote down, I'll have my formula sheet, and I'll have this other stuff if I really need it. So that's for exam 1, though, is closed book, closed notes, except for your study sheet.
When is exam 1?
We talked about it at the beginning. It's either next Wednesday or 2 weeks from today. We're going to vote on it, though, under the benevolent dictatorship policy that I forgot the name of last week. There's pros and cons to it, though, but we already walked through that a little bit, and we'll come back to that. So the case of multiple order polls is when things get messy and turn into a real difficult task. If you have a poll that's repeated, so the book uses S as the repetition factor, not to be confused with complex variable S in the Laplace transform, but so a poll is repeated up to S times, so this term here is going to be S in the limit, it goes up to S. Then you have to get your so-called residues, and residue is a term you might hear me say because in complex variable theory and Cauchy's theorems, the residue is exactly what we electrical engineers think of as expansion coefficients. Same idea, though. So AK you'd get from this formula, and then the CMs on a repeated poll are gotten from this blue boxed equation. It looks nice because there it is, all in one compact form, but you have a factorial thrown in there, and the nasty thing is you have to multiply your function x of z by replacing z by w to the minus 1. So this goes in place of z, and you also have to multiply times the pole term that you're solving for by replacing z to the minus 1 with w, and then you have to take the z minus mth order derivative of that whole thing. So it's a rational function. You know you can do things like that from calculus, but is it fun? I mean, you have the quotient formula, right, for taking derivatives. And then you set w equal to the pole term to the minus 1. But, we'll look at it here initially, and then I'm going to show you on scratch paper what I'd recommend that you do. You do have one homework problem that has this in it. The chances of the exam having a poll higher order than 1 is about 0. I just don't want you to mess around with it on the exam. And you might already be saying, why do we even have to do this? Well, it's kind of, maybe it's, in some sense, you'd say it's a rite of passage that you know how to do this, but it also is just getting you familiar with the mechanics, because we do have computer tools, which we'll show you later. The residue z function in Python is like what MATLAB offers. And you could just say, if I can get the pole 0 plot, I have an idea, and we're going to learn more about that in Chapter 5, about what are the modes in the system. So what are going to be the transients and frequency responses due to the pole and 0 locations, and just let it ride. I mean, you'll just simulate it using L filter. You just run signal through an L filter, and you can do freq z to get the frequency response. So you're not always driving at this inverse Z transform. It's actually not super common to want to do that. But if it's important for some modeling that you're doing, you know that it can be done. And of course, if you've got several multiple order poles, then you'll have several of these expansion-like terms for each multiple order pole. I never have had to go there myself, but it can be done, right? And like I said, residue z is pretty powerful at just bashing through all of this. It's calculus under the hood in the blue boxed equation, but this is polynomial derivatives, and polynomial derivatives you can program on a computer. You've probably never thought about doing it, but you have a routine you go through, right? So you could make the computer do that derivative, and that's really what residue z is doing. So when you have this as the basis, now you can just start working problems. So we'll assume, also we have to assume that if we have had to do any long division, the factors BR z to the minus r from long division is just going to inverse transform back to BR times delta of n minus r, because we know that this inverse Z transform is just delta of n minus 1, and that's right up here in our table. That's the second entry right here. And if it's the simple pole case, then we just have the things we already looked at the last 2 weeks. We have, those are the inverse transforms, depending upon whether that pole is from a right-sided sequence or a left-sided sequence. So you just have to plug in accordingly. Be on the lookout for that, though. Don't get careless and forget about that, because it is going to give you a wrong answer. If that pole was a region of convergence that was the interior, you need to use the second one. If it's the exterior, then it's the upper one. And the book throws twists and turns at you with left and right-sided sequences. It's just trying to make you strong at solving. So this first example is just a second-order system. M and n is equal to 2, so we have to first do line division. And I don't think anybody ever liked doing division longhand, no matter what it was, right? I mean, when did you first do that? 3rd grade maybe or something? Just a guess. But polynomial line division is even a little bit more bizarre, but it's still founded in the same idea. You just look at, pardon me?
The coefficients up and below.
Yeah, you look at what you have to do and what you want to do. This is your numerator right here. I just reordered it in the opposite order. And what you want to do, the whole business of the line division is you want to reduce the order of the numerator by 1. So that's why we're focusing on z to the minus 2, and we want to make sure we get a z to the minus 2 in there, and that's what this remainder is. 2 times all of this will give this row, and then we subtract, and there's our remainder. This is our remainder, 5z to the minus 1, minus 1. Then that sits on top, and the 2 is factored out. So that's our line division. So now what the problem reduces to is just inverse transforming that and setting aside the 2, because when we get all the way down, we just bring the 2 back in, and that will become 2 times delta of n later. And then these 2 terms, once we have A1 and A2, will come back using either this result or this result. So the first step in actually applying partial fraction expansion is being able to root a polynomial. And one of the homework problems that I've graded from one of you, somebody did a quadratic formula and didn't get it right. So you might have to review that. What I would be more inclined to do myself is just be kind of lazy about it. And I mean, you can always do this. I'm running, today I decided to bring up Jupyter Qt console since it's kind of small sitting here. And I can go signal dot r, and I'm looking for residue z. So you can see that's one of my options there. And then, actually I don't even need to use residue z. I'm just going to use roots. And then I would just put in the coefficients that I have here, so that it would be 1 comma minus 3/2 comma 1/2. Oops. I'm thinking of a different language probably, so I need to put in a square bracket. it has to be an ND array, which this function takes it from a list in Python to an ND array. Okay, so the roots are 1 and 1/2. More typically, when I'm working these problems, I'll just guess, because I'll say, I can kind of get a feel for what's going to go on there from the quadratic. But pick your way you want to do it. When you're doing the exam, you're going to have to not have, you'll have a calculator, but you won't have Python sitting there running in front of you. I mean, because I put Python, I installed the 4Pay app on here called Juno. I do have a full Python on my tablet, but I'm not assuming everybody has such a thing, so I'm not going to allow that. But you can have a calculator, and if you have Texas Instruments, one of those that has the roots function in it, you know, you could check that if you wanted to. These are all things I leave up to you to do. I don't want you going on your cell phone, though, onto the internet to use Wolfram Alpha or something like that. Matter of fact, I don't want cell phones out at all. Calculator can be out, and your crib sheets will be out. So at any rate, I know what the factors are. The root is at 1/2, and I have a root at 1. So now I just use the residue, standard residue or simple pole coefficient formula, set it up, do the multiplication by the pole whose residue I want to find, and when I do that, I cancel that pole out, and then I just substitute in. That pole is located at 1/2, and then I get -9, and I get 8. And then I put it back together again, and I just go to the tables, and this was, you were told in this problem that region of convergence is the exterior of a circle radius 1. So this piece of information is used absolutely to get the inverse transform. That's your key, remember from last week, to tell you whether it's left or right-sided, which poles are which. These are both equal to 1, and oh, by the way, that's also useful in rooting the polynomial, because if that's the edge of the region of convergence, what does that tell you? Please answer for me, so I'm seeing if somebody's thinking. If it's got to be greater than 1, what does that say?
It has to do with the unit circle. If it's not,
Well, it has to do with whether it's the maximum or minimum pole radius in the system, right? If it's the exterior, the region of convergence is the exterior, that must be the largest pole radius. And there's no annular, it's nothing inside. So there's 2 poles in this system, one of them must be at 1 or -1, right? That is not a guarantee that it's at 1, but it's either 1 or -1. Does that make sense? And then there's another root that's got to be smaller than that, because that would be the largest one. Good?
I have a question, Doctor.
Okay.
I remember last week you mentioned about not canceling for when doing the inverse, but here we are already canceling one of the terms out. Is that?
What do you mean canceling one of the terms out? When we do the residue?
Get rid of the z to the -2.
Well, it's because we're using a residue formula. We're doing this thing right here. This is what we bring on next to x of z. This is the coefficient we want to get. AK goes with this dk, so we multiply that in the numerator and it will cancel it out in the denominator, right? And then we're making the substitution to get the coefficient. I know we come from different generations by far. I got beat up on circuits. I mean, circuits was the first hard EE class to take, and it started your second year, because your first year was chemistry and physics and calculus, and in those days we took mechanical engineering classes too. We took statics and dynamics. Eventually I took thermo and heat transfer and mechanics and materials, believe it or not. Those are all the ME classes that I took. We had a certain number of ME classes we had to take, but we didn't start circuits till the second year when you were well down pathway of calculus. So the idea of partial fraction expansions and just working these types of things became the huge big deal, because we also had, I guess, had differential equations. I can't remember when that was taken exactly, but we did lots of partial fraction expansions in circuit theory, which you still do that today, but you don't probably spend forever on it. You spend a certain amount of time on it, though, right? Okay, so back over to this problem, we get -9 and 8. We know both of those are poles that are right-sided, correspond to right-sided sequences, because you know the region of convergence is the circle of radius 1, and we know that's true. So we immediately look at what we've got there. We've got a pole at 1/2, a pole at 1, so we know both of those are included in the right-sided terms. We inversely transform, and then we go ahead and just grab this from the delay theorem, or delay property, and have 2 times delta of n. I just threw in another expansion on this example saying, suppose the ROC was less than 1/2. So the poles were at 1/2 and 1, so if we say the ROC is less than 1/2, that says both sequences are left-sided, right? And that's the solution that I give here. And then the mixture case between 1/2 and 1, that would say that the right-sided sequence is the pole at 1/2, and then the left-sided sequence is going to be the one that's at 1. So you get a mixture of two different directions. Second main example here is going after a system that has one repeated root, and this is kind of the motivation for being able to power through the one homework problem that does all that stuff. Let me just open up my tablet so I can go look at where I know that problem is. You're probably thinking, what problem do you think it is, if you've already worked on it? Problem 6, text problem 3.32a. And don't do any other parts of that problem. That's another thing some people did in the first homework assignment. They worked all the letters. They didn't work just a few of them. So at any rate, that's the one I'm thinking of. So it's got 2 single poles and then one repeated pole in it. And the numbers work out pretty weird. They're ratios of integers, though, but they work out kind of weird. Things like 108 over 49 minus 32 over 25, things like that. And when you do this in Python using residue z, you will get decimal numbers. And then you have to see, is my number correspond to that? So you just divide it out and see that it should be essentially very, very close to get that. So this example pertains to that. The only thing that's different in the homework problem is there's an extra pole out here. So there's 2 single poles and 1 double pole. So you end up having to solve for an A1 and an A2, and then you have a C1 and a C2 for that problem. But here we have the single pole and then the repeated pole, so we have to solve for both C1 and C2, and the standard residue formula works for solving for A1. We just multiply by 1 plus e to the minus 1, and then we're just left with, after we do that multiplication, we're just left with the denominator and make the substitution, we get 1/4. Then we go on to use the blue boxed equation to get C1 and C2, and C2 ends up being very easy to get because we're basically just going to multiply both sides times 1 minus c to the minus 1 squared. So when we multiply that up over here, we're going to cancel that term entirely, and we can just solve for C1 or C2 straight away, or as the formula says, it would be doing this. But because there's no derivatives involved, in the end, we can just solve for in the end, there's no derivatives involved. I mean, that's C2. We can just get 1/2. I will maybe walk through that here too. I've got a, it'll open up. I've got this scratch paper set up to kind of work this in an alternate fashion. And then to get C1, we can go through the formula with the derivatives and the substitutions to get 1/4. So this is the messy part, in my opinion. I mean, it only gets worse when you have more terms in there, and in the homework problem, you have enough stuff going on in there for sure. So let's take a look at how we do that. In this case, though, if we just move forward with the way I have it written out here, you just put all the coefficients into the partial fraction expansion representation, which is, right up here, A1, C1, C2. And then the only thing that's new is we have to recognize that this is how we're going to inverse or table lookup the inverse Z transform of the 1 over the repeated pole. I'm going to develop this result from a theorem that comes up a little bit later, but we'll be going through that soon. If you were having to do this cold turkey, in other words, not having seen that before, you would have to go up here to this table, and you would say, is it this guy right here? And in fact, this is the universal answer for any number for k repeats, but I made life easy, and I put in the special case of 2 repeats. And the only difference is here I have it as a times e to the minus 1, and then that alters things just slightly, but I'm going to take a look at that in a few minutes when we go through this theorem. But you would be looking it up from here. Since I'm telling you that chances are about 0 that you will have to do anything like this on the exam, putting this blue boxed result in is not something you'd want to put on your crib sheet. But if you're worried, put it on there just to have it just in case, right? So now we can inversely transform that back to the signal or sequence x of n. So what I want to do right now is just go over to this scratch paper. And what we already have, I just have to look at this again. From this, we already have A1 is 1/4 and C2 is 1/2. So to get started on this, the first thing that you might not remember from partial fraction expansions are that you can get C2 pretty easily, because C2 would just be would just be that, and if I multiply that out right here, I'm just going to have 1 over 1 plus e to the minus 1. So I get 1/2 immediately. Not any fancy formula like I have in the notes and is in the book, kind of a do-it-all thing. I mean, do-it-all equations, you'd say if I just had that, I'd be in Fat City because I could do everything with one formula. But then you delve into it and you say, wait a minute, this form is messy and complex. I have to wade through all this calculus steps to make sure I don't make a mistake. So this just tells you that you can always get the coefficient with the highest power of that particular pole, the highest number of repeats, by just doing this formula. And then the next step is, how are we going to get C1 without having to resort to the other techniques? So the standard technique would be this. I will take what I've got already solved. I've got 1/4 and 1/2 done, so I can write this out. I'm getting a lag right now, so I'm getting a little bit faked out. So I have to solve for C1. And what I'm going to show you right now, if you have a technique that you learned in circuits or math or something, and you like it and you know it works, I'm not asking you to warp your brain into thinking this way. But I'm just going to show you something that you probably have already seen. And this works for multiple coefficients. If I didn't want to solve for C2 right away, and I didn't want to solve for A1, I could write something like this out with all those coefficients unknown, and then I can pick values of z to substitute in on both sides, in x of z directly, and then on the right side, as long as the z values I choose don't make any of those denominators singular, right? And then you'll have a system of equations. Then you'll have 3 equations and 3 unknowns, let's say, or 2 equations and 2 unknowns, or what we've got right now, we just have 1 equation that we'll write and have 1 unknown. Sound familiar? Is this jogging your brain enough to say, I've done this before? So what value of z should I substitute in? What's the no-brainer choice? You can pick any value of z. I would pick it to be a real number, and I would just make it be the easiest one to work with. Yeah, okay. Well, 1 doesn't work because 1 would blow up, right? So really you're forced into taking z is equal to 0, or z to the minus 1 equals 0. So make that be the substitution. So from over here, we're just going to have 1 over 1, and then we'll have and that's just going to equal 1, right? And then on this other side, we're going to have 1/4 over 1 plus 0, which is 1. We're going to have C1. Then we're going to have 1/2 over 1. And so then we pull these things over to the other side. We have 1 minus, we have C1 make sense? And just to go back over here, okay, 1/4. So I'll leave it up to you to decide how you want to do it, but we're not reinventing the wheel in this class. I don't want you to just learn how to go through the mechanics of something that's messy. Just cut to the chase, basically. Just, you're sitting here, you're going to angle right over there. You're not going to take a long way to get there. I do want to encourage you to check, though. So we'll talk about that in a couple of minutes here. So moving along into other types of inverse Z transform, suppose we have a complex conjugate pole pair. This is something that I remember in circuits 2 came along probably in the same order in the S domain, but now it's in the Z domain. So suppose we have poles that are on complex conjugates. So and then I'm going to have a 0 and another 0 there. What I've done in my head is I've just said what would be the pole 0 plot corresponding to that numerator. I multiply by Z squared top and bottom to get positive powers of Z for the sole purpose of clearly seeing where the roots are, where the poles are, where the zeros are. So I'm going to get in the numerator a 0 at Z is equal to 0, and I'm going to get another 0 somewhere, maybe most likely on the real axes, because I'm going to assume the coefficients aren't complex. B1 is not complex. And then in the bottom, I'm going to have a complex conjugate pole pair. In this case, I'm showing them inside the unit circle, so that way the region of convergence will include the unit circle, and it will be a stable signal that will be a damped sinusoid of some sort. So the partial fraction expansion formula, the main addition here is that we have distinct poles. So we have the same residue or coefficients formula, but we have a property that's proven in this next block of math here to just say that AK and A sub KK are going to be conjugates of each other. And that should come as no real surprise because the roots are conjugates of each other. So that just tells us that we can proceed with that thought in mind. We know we're going to have conjugates. And we go ahead and take the inverse transform back, then we can write it in terms of complex exponentials, and exponentials are R sub k to the n. That would be, I think I've got it written down here, yeah. The roots have some magnitude and angle alpha sub k, R sub k and beta sub k, and then the coefficients have some magnitude and angle alpha sub k. So you can put that together into a cosine, is the way I did it, and then you have an angle associated with it. So you have a damped cosine. I said damped sine, same idea, just depending upon how you want to write it. I guess cosine is probably more familiar to me in the way I've got the notes written out. So this blue box just tells you what that is for this particular case. But if we go back up to the table, you're saying it's got to be in the table. So I don't have to write this down. It is in the table, but it's in the table as this special form where it's either purely cosine with no phase shift or purely sine with no phase shift. So what I've done is I've said, well, the numerator is going to be different for cosine than it is for sine, but in general, if you have an arbitrary numerator where the coefficient here is some generic thing, then the added value, I guess, in what I just did is that it tells you under all circumstances how it's going to come back to a cosine with some angle, and then the A sub k and R sub k are going to come out of that, and the beta sub k are all going to come out of that. So this, yeah, if you want to put this on your crib sheet, this might be good, because this actually handles a very generic case, right? I generally don't give a problem that has this in it either, because it's just messier. But when I say modes of a system or modes of a signal, this is an example where there's a complex conjugate pole. So if this was the impulse response of a discrete time model of your car's suspension system, let's say, that would be second order, y second order, back in physics and mechanics, you learn about how you have a spring, a damper, and a mass. Remember that vaguely from physics? And when you excite it, like give it an impulse, which would be like going through a pothole or something, that combination of those three items, mass, damper, and spring, is going to oscillate and then decay down to zero. So that's what this type of response is. If it's a lossy system, it decays down to zero. It's got that mass in there. It doesn't have just the damper and an ideal spring. If we like thinking about circuits, which I actually like better, but mechanical things always seem to be more real, then I think of the mechanical side of it. But in circuits, it would be an inductor, capacitor, and a resistor that would get excited by, say, an impulse, and then we'd be getting this sort of damped sinusoid kind of a response out of it. So the modes are some frequency beta sub k that's controlled by, in my picture here, it's controlled by the angle that these poles make to the positive real axes, and that controls the oscillation frequency. And then there's a phase shift associated with the complex part of the coefficient. And then in the solution, there's a phase shift to combine sine and cosine into a phase shifted cosine. I've got a simulation of this in the Jupyter notebook too, which we'll look at here pretty soon. So here's an example where this bears out. It looks like if you were to see this problem, and this is where I want you to be very careful, obviously in homework, but especially on the exam, you look at this and you say, there's a denominator. You see no ROC, so this is fair game in Oppenheim and Schaefer terminology, and in my exam writing terminology. The ROC is not given, but the causal information is what's going to translate into the ROC. If it's causal, we know that it's a right-sided sequence that comes back, and we know the ROC is going to be the exterior of something. So I'll just say R1 or R2. Actually, let's just do it like this. Sometimes I don't like the way this sort of works, and it just bumped me out. I'm just trying to be more precise here to say that, and it's not even going to let me do that. Okay, what is it? I'm clicking on the tool, but I'm not using a single thing with this, and it's drawing something for me. Thank you for doing that to confuse me. I don't know what's going on. I just wanted to say it's going to be greater than the maximum pole radius. So I don't know what that is because I'm not assuming initially that that denominator has got real or conjugate roots. Okay? So you would have to go look at that. You would have to examine it. In this problem, I've already done that. If we were to go back like I was doing over here, I see, must be, did one of you write Slack a message to me? Okay, because there's one person that's still not here. I could go over here and do just like I did before, and I could go plug the coefficients in. I've got 1 minus 1, and I've got 1/2. So you see that your eyes bug out and say, I got to deal with complex coefficients. So there they are. If If you change the sign in this very easily, though, it will go back to real coefficients. So just be careful, that you don't make more work for yourself by having complex coefficients. So in this case, it's no lie, it's there, it's complex, so we invoke this thinking. We're going to have one coefficient, and we're going to be able to plug in and get that coefficient pretty readily, and then we can find the angle, the polar form of that A1. We can take D1, which comes from the roots, to be 1 over square root of 2 e to the j pi over 4, and then finally you can put it together just like this. And then you could model this in Python, obviously. If you wanted to just do it that way, you could do it all by starting in residue z and then taking the coefficients out and putting them in to this equation right here to have it plot, say, a picture. And I think that's exactly what I do in one of the examples in the Chapter 3 notebook. So power series expansion, it's just, I'm documenting what it is. We know that on the sequence side, when we're finding the z transform, we're effectively saying that x of z is a power series on the right-hand side. So if we keep that thought in mind, it says that if we can obtain a power series expansion of x of z, then we can term by term identify the inverse z transform. So in this case, if x of z happens to look like this, we don't really have to do anything sophisticated. We can just simply say, if that's all there is to it, I can just inverse z transform that term by term already. And that's kind of a super simple version of the power series expansion idea. If we had 1 over 1 minus a z to the minus 1, and we didn't know anything else about the power series for that function x of z, we could go ahead through line division and get this solution. We'd have a remainder, but we could just start, speculating that if it's causal or right-sided, that we're just going to do the line division to pull out negative powers of z. And from that, we'd be able to then construct the inverse z transform, and then through geometric series, we know that it's just going to correspond to a to the nu of n because of the way that sequence would correspond to a geometric series type sequence. A more powerful version of power series is where you actually have a transcendental function like natural log. You can go look up the power series expansion for that, and then you could inverse transform term by term each of those terms up here and get x of n. I'm pretty much just showing that to you like I showed you a difference equation that competes for the square root. It's not something you're going to be ever having to do in this class, but it's possible that you can do things like that if that was part of a problem you were working on. So now what I'm going to do is just look at a summary here, and I'm going to take care of all of these right now. Just get them rotated. If they will stay rotated. Okay, so the idea with this is just to kind of summarize certain things that we've observed so far about the z-plane, the pole zero plot, the x of z, and then going back to the sequence domain. So if we have, say, a single pole on the real axis, we know that if it's the positive real axis, it's it's going to be an exponential decaying, starting at n is equal to 0. If it happens to be in the negative real axis, it's going to be an alternating sine sequence for that particular signal. If we happen to put the pole right on the unit circle at z is equal to 1, then it's a step function. If we put it on the unit circle at z is equal to -1, it's an alternating ±1 type step signal. If we put the pole greater than 1 or less than 1 still on the real axis, it's going to be an exponential that either grows as a steady positive value or expands as an alternating positive-negative value. These are just things that can sit in your mind and say, when I see behavior like this, I have a concept about what is causing that. If it happens to be 2 repeated poles, we're going to get an exponential that's going to be a mixture of n and a to the n. We saw that earlier, but it's going to be a linear term and a exponential term, but the exponential term is going to dominate, so rather than having the linear term of n somewhere in the sequence causing it to blow up, the product of that with the exponential is going to bring it back down, so it rises up and then it decays. If, however, we put both poles on z is equal to 1, we're now going to get a ramp because we have n times a to the n, but a is going to be equal to 1, so we just have n inside of our transform, and we're going to have, when we actually solve it, we're going to have an n plus 1, but it's going to be a pure ramp or an alternating sine ramp. And this holds true in, of course, in the S domain as well, in terms of things we expect to see happen. This would be the case of an accumulator or an integrator, right, where we put a delta in and the output is going to be a ramp. We're actually going to have 2 accumulators. The first accumulator will accumulate the delta to a step, and then the second accumulation on the step will convert it into a ramp. So it'll be just rising up like this. And if they're outside the unit circle, it'll be expanding as n goes on. And then the conjugate case we were just looking at, if the 2 poles were inside the unit circle as conjugates, we get the damped sinusoid. If we put the poles right on the unit circle, we can actually build a digital oscillator this way that will oscillate perfectly at a steady amplitude sinusoid. I can't say I've explored this lately, but I have done it in the past. I've actually had people do it in the real-time DSP class before too, in the processor, in the microcontroller. It's not maybe the ideal way of creating an oscillator, but you create it with a difference equation, and you set the coefficients in the difference equation to make a system that's actually unstable. The poles will be on the unit circle, and it will start oscillating. And if you put them outside the unit circle, it expands greater and greater. When I originally wrote my notes, I was reading other books, and these ideas came from some of the other books I was reading, just to have a visual. I think this is helpful when you're working on systems. And for me, I'm always building simulations in Python, and I might put something together, then I put in a test signal, and if I see something like this happening, I'm saying, what did I just do? Did I really want to do this? And I'll see, the waveform will more quickly register in your brain like, oh, I put the pole in the wrong location. I'm getting an alternating sequence. Oh, I put the pole outside by setting the coefficient wrong, and now I've got roots that are greater than 1, so it's going to exponentially grow. And if you're curious, last week I had, this big simulation presentation, architecture review. It all has gone well. I put lots of hours into it. And just to let you know that I definitely make my mistakes, and every day I'm reporting on things that I've done since then, and I try to add something new to enhance the model, and I usually break it it doesn't work right, and I have to go back and see what is my coding error and fix it. And it's getting more complicated because it's object-oriented Python, so I have multiple classes involved now, and I have lots of variables that are held bound to those classes, and it's pretty cool the way it works. Now the question in my project will be, can one of the FPGA developers take that and build his implementation to run in VHDL, which is what he's going to be doing it in. But he's going to have a Python simulation. He can tear into it and see that it's built up with classes. So you've got these classes that are the main elements, the main movers that show up in the block diagram, and then the methods carry out different things with the bound variables to implement the complete system, so he can go study the code. Okay, now we're going to jump to just kind of start the wrap up. I think I'll take the break now. It seems like a good time to take the break. So when you take the break, and by the way, this projector is new. I'm going to find out today if it's going to quit. I have to give a report. While you're out on the break, though, remember, and only 2 of you were here at the very beginning when we were starting the class, we're going to have the exam either next Wednesday or 2 weeks from today. And we're going to talk about that immediately when we come back, so I know how to direct my energies for the rest of the class. So be thinking about the ramifications. And if you want to read more about it on your phone or something, go to the website, and I wrote a little note in on assignment number 4. I put a paragraph in there that just explains what my plans are and the fact that solutions are already posted to old exams on the website too. So I'm going to go pause my video. Okay, we're back to the session again. We're going to be looking at how we can use Python to check the inverse Z-transform homework problems, and then we're going to move into looking at some other things with Python, but we'll do that after we move downstream and look at the one-sided Z-transform. There's a lot of material at the end of this chapter that we're not going to be really covering. It's just in there because I had it in there when we used to do complex variable type stuff. I will be looking at theorems and reviewing certain theorems that we haven't taken advantage of. And since the one student is out, I'm not going to talk about the exam just until he's back in the room. So if we want to do an inverse Z-transform using Python, we have this function called residue Z, and it's in scipy.signal. So we'll have to use signal.residueZ, and then our primary means is just putting in our A and B coefficient lists, or ND arrays, if you want to think of it that way, for our particular problem that we're working. We're going to have a ratio of polynomials and negative powers of Z, and we put those in. And there's kind of a disclaimer on this whole business, and that is that it has to root the polynomial. It can possibly go awry with a real extreme case. None of the problems that we have are that extreme case. So you shouldn't have to go in and add these extra arguments that are optional. I'm just using B and A, and it's perfectly adequate to get the job done. So what it does is it takes this rational function, doesn't have to be proper rational. It will go ahead and do the long division to make it proper rational, and then it will return, they call it residue, as in partial fraction expansion coefficient. So R is for residue, if you want to think of that. And then from long division, it will get out in an array K the term that's just a constant, and the next element of the array, K1, is Z to the minus 1, and so on. And then it also returns the roots as another array. So PI, or P, is an array of the roots. So when you're using it in practice, you're dumping into it, and you're returning from this function all three of those variables, and so I have to remember what that is. Look at an example in a second, but I would just go I already did this a little while ago. And there's the help for it right up here. This is in Jupyter Qt Console, which I installed on top of the other stuff I had you install. And the biggest thing here is how do we output stuff from it, and it doesn't quite show that. There's a way of seeing all the help right here. I'll have to go to Jupyter Notebook. It's a little bit easier to see all of the extra helps from that. At any rate, now that we're all back, let's have the discussion about when of these two dates you would like to do the exam. And remember, the term that I didn't remember last week is benevolent dictatorship. So I have the final call on this. I'm fine doing it either way. I do have a little bit of a desire to just do it later so that you can have more time to absorb what you're turning in on Friday on this homework. And of course we'll get the solutions posted, but it ramps you, it puts a little bit more pressure to have it all ready to roll by the 16th. Not impossible, and I'm prepared to do that if that's the desires. What's going to be happening, though, is we'll start sampling theory at the end today if we don't have the exam on the 16th, because I won't have to do the reviews until the 16th. And then you'll be having that run in the background. You'll start working on that assignment as time permits, and especially the day of the exam and after it, you'll be working on those problems. And right now they're due on Friday the 1st. It's the entire sampling theory, less the random processes and things that also is included in Chapter 4 notes. So that's why that's due after. I don't want it to interfere with the exam. It'll just be set aside, sort of put on pause, and then come back to it. The other thing that I'll just give you before we vote, what's going to be happening before the end of this month is I will be getting the project number 1 figured out. It may not be the same as I did 2 years ago, because I've changed one problem usually every time I give it. I have to decide. I haven't had you do anything with Julia, so I'm not sure I want to have a Julia problem on there. I did C++ the time before that. I don't know. I've never really asked you whether you like C++ or would like to try out C++. I give you all the files, and that would run out of Visual Studio Code. We'll discuss that more the next couple of weeks, how I'm going to put that together. But that is going to come out in this interval too. And I realize you're going to say, wow, we're loaded up. Yes, you're loaded up, but you're going to have it at your disposal to decide what you want to start working on, because you're going to be multitasking, right? Either studying for the exam, working on homework, or starting to look at a project, which will be a sample Jupyter Notebook, and so on. So hands, or what's any interest? I know when you were here all by yourself, you told me you had something on this day, but the whole day is not dedicated to the exam either. It will be, usually I will lecture for about an hour until 9 o'clock. We'll take the break early, and then you'll come back, say, about 9:15, and then you'll have until 10:40 to do the exam. I just can't make you sit still writing an exam for that long, and I don't want to give that time up either. So, thoughts? So that sounds better, okay? I know you have your work thing.
Yeah, I prefer the 16th because I can't be here on the 23rd.
Okay, so if you can't be here on the 23rd, when would you take the exam if that's what we go with?
16th. Or if you
the 16th, I would not give it to you during class time, though. You would have to come take it after.
I could do it other time, like, if possible.
Yeah, it could be the 24th. I mean, I'm working from home And I could, assuming the weather is nice, I could ride my bike to campus and I could sit in the lab and probably bring my work computer with me and work while you're taking the exam. That can be done. We have to know and make sure that it will work. And then you have to, suppose you decided to take it on the 24th, let's see, I guess that's okay. You take it on the 22nd, we're in class, and you would leave at 9 o'clock, and you would never talk to anybody. You have to be, the obvious thing is, why would you want to say anything to anybody else, right? But that could be done too. Yeah, and vice versa. If you're in here taking the exam, and I'll say there's one student who's not even going to, you're not going to be here at all on the 23rd. Okay? But still, you're floating around, so you people don't start Slack messaging, that was a really hard problem, or that was easy, or blah, blah, blah. You just have to be quiet about it. I'm inclined to go with the 23rd. It makes life harder for all of us, but I think the majority rules, unfortunately, for your standpoint. I've done it this way most of the time myself, so.
I can talk with you that.
We will have the review, though, the old exam problems next week, and everything will proceed, and your frame of mind, I think, will be clearer to wait it out a little bit anyway. I mean, that's what the other three are arguing, and the number 4 or number 5 who hasn't chimed in, except I'm assuming that that's him on Slack, but I haven't looked. Would probably go the same way. He's the one that's taking the lab, so I'm going to find out today if he's going to be in lab. Okay, so I'm going to proceed, and hopefully we'll start sampling theory, which is one of the most new-oriented chapters. Part of sampling theory is going to be stuff you've seen before in 2610 and 3205 maybe, but there'll be a lot of new stuff, and there's a lot of practical things. And then the random process stuff is going to be a little bit challenging, but it's important so we can understand quantization and noise in signals a whole lot. Everything I do has got noise in it, or an interference, or a jammer, or something. So, okay, so back to where we were. We're talking about using residue Z, and so the simple starting point is just the very first problem that we did. We first had to do line division, and I'm just going to stick in the notebook in the notes here, and I'll jump over to Python a little bit later because everything's documented here. Actually, if you're seeing how this was done, I actually did this. I did everything right here in the Qt console because it tends to group things together in pairs, and it gives an output that kind of looks exactly like, well, I guess in this case it isn't, but there's some examples here in the notes where I did it in the Qt console. And I think I told you that this actually came first for Python. Jupyter was not formalized immediately. It was called the IPython notebook, and then there was IPython itself, and then a Qt version of the IPython console was created, and then finally Jupyter came along a little bit later in the history of all this stuff. I felt like my years of going to the Scientific Python conference down at UT Austin was pretty significant. I was there for the unveiling of a lot of new things that, engineers were very technically motivated. This is not just engineers, it's the whole scientific community, data science, machine learning, everything. But when all this new stuff was being released at the forums where all of us were in the same big room at the same time, there was a lot of excitement, people clapping, people cheering. I mean, it's like, that's very unusual, right? Nobody would do that except when you're excited about tools for doing your work. In retrospect, maybe it seems bizarre, but, it's the way it happened. So, okay, so back over here. So what I did in this case was this problem is trivial to do with residue z. You just load up the coefficients. 1, 2, 1 goes in down here, and then the 1 minus 1/3, 1/2 goes in down here, and then you pull out residue array R, the poles. It will root the polynomial in the denominator to get the poles in coefficients, and then it will get k if k is needed from long division. So in this case, I just have it list out what R is, so the coefficients are -9 and 8. We saw that earlier today. The corresponding roots are 1/2 and 1. So everything is always in one-to-one correspondence. If you're going to go back and reconstruct your problem to actually go back to the time domain, you would say this -9 goes with a pole at 1/2. So that's this piece right here. And then the 8 goes with the pole at 1. And then, of course, there is this first coefficient in k, so that's just 2 all by itself. And then, bang, there it is, just like that. So what I want you to do for the homework, I would like to have you check things. It's a good self-check to see if you made a mistake, especially the longer problem, the one that's more complicated to do. So this is pretty nice and simple to do. Here we could take the next problem. Which is where we had one repeated root. And again, we're just going to dive in and do it. Now I'm going to do a little bit of technique. Since this was not multiplied out, you can just multiply this out by hand. You could take this polynomial times the second degree polynomial and then, collect terms and do all that other stuff. A known fact about polynomials and convolutions of the coefficients of polynomials is that there's a one-to-one correspondence there. So I'm using the convolve function that's in scipy.signal to just say, let's convolve a polynomial that has coefficients of 1 and 1 with another polynomial that has coefficients of 1 and -1 and 1 and -1 a second time. So I'm actually doing a convolution wrapped in another convolution. So I'm just being kind of lazy, but I'm just going to do that polynomial multiplication using convolve to get the coefficients back. So I just loaded that blindly into residue z. But if I wanted to do it, I guess I could, oops, I can't grab it here. I mean, if I wanted to do this, if you're not comfortable with it, what I would probably do is I would probably just do might just try one. So that's polynomial 1 plus z to the -1 and 1 minus z to the -1. Oops. I didn't spell right. Okay, so there's the coefficients 1, 0, -1 on our second degree polynomial. And so you could just concatenate that again with another one. And that's what I was doing here. Matching parentheses is handy here. So there it is. 1, -1, -1, 1. So that takes me all the way up to a third degree polynomial. And then that's what's running inside of here when I'm doing the residue z. I've got that third order polynomial, and it just guts it out and it says these are my coefficients or residues. So don't get confused. R is residue, not root. P is pole. So residue coefficients / coefficients, 1/4, 1/4, 1/2. We saw that earlier. And then the roots are at -1, and then there's 2 roots at +1 from this expansion development. And there's no long division, which we did not expect, right, because it was proper rational. So then you can just go ahead and write that down here, and then inverse transform term by term. Let's just go over to the notebook right now, see what else I threw in there. Besides all these examples, I also did the one with the complex conjugate. So I just loaded this one in directly, and then when I run it, I just listed out all of them together, A, P, and K. I called it A rather than R like I did before, but the A array has these for the 2 coefficients, which are conjugates of each other. Here's the residue, here's the poles, and then no long division. So I could go ahead and use that to get an analytical solution if I wanted to. But here I just said, why don't I just do this numerically, take it all the way through? And what I'm doing here is I'm just saying, if this was a signal, and I wanted to see what that signal is, I could view it as driving a system with a delta function, and then the system that it would be going through would be this rational transfer function. So I'm just sort of redoing the math to say, how would it be if I convolve the inverse Z transform here of this x of z with delta of n as if I'm driving it through a filter using the LCCDE or L filter. So that's what I've done down here. I'm just going to take and pass an impulse on a 20 sample integer array n, put in the numerator and denominator, put in my input u, pass it through, and okay, something didn't happen. Okay, so here what I did is in this plot, I took the theoretical result that we developed earlier and just ran it out using the same integer index n, and then have the experimental or simulation result done, and I'm just comparing them visually at least. They look identical. Good? Okay, we'll come back to this with the one-sided Z transform here in a bit. This will be interesting, but I'll just, because it's very tempting for me, this is like the most important thing in this example is how I can use initial conditions and my understanding of the one-sided Z transform to provide continuity between data frames in a long simulation. And this will also be utilized in the Pi Audio Jupyter Notebook things you're going to be doing, because you're going to be taking frame after frame of data. You'll be managing states between one call to the next call. And this is one of the essential elements of real-time DSP, that you will process either a single sample every time an interrupt fires, or you will process an array of samples, like in a buffered frame-based simulation. And the frame-based technique applies to using your PC's audio subsystem to process frames of data. Okay, so this will go pretty fast. Z-transform properties. we had this at the very beginning, just saying an arbitrary relationship between a sequence and its Z transform is just the double-sided arrow with the script Z over the top. So with that thought in mind, we have linearity, and linearity just says we can Z transform a superposition of multiple sequences to go to the Z domain and back again. The only caveat is we have to consider the region of convergence as being the intersection of the individual regions of convergence. And this does show up in some of the homework problems where this sort of thing is going on, and you have to bear in mind that this is going to happen. The region of convergence can have something very interesting happen on this side, and that is that individually there's going to be poles associated with x1 of z and x2 of z. But when these two ratios of polynomials come together, the numerator might have some zeros in it that will cancel some poles out. So be on guard for that at all times, because Oppenheim and Schaefer problems tend to slip that in regularly. There's a pole zero cancellation that would be happening. It's probably more in Chapter 5 when we'll be revisiting some of these things. Okay, the time shift theorem, very useful. If we have a z to the minus n naught that's factorable out in front of an x of z, that just says that our sequence has been shifted by n naught samples. And a good simple example is this one. You identify this as being absent from a table, so you set that aside and say, oh, what remains is the 1 over 1 minus 1/4 z to the minus 1. That just should be 1/4 to the n u of n, and I can do that directly. If I didn't want to do that, I would have to do line division, and that's what I did here. So I have the line division result, and then I can get these two pieces, and this is where I started seeing some things in grading set 2, where you get a form that looks not like the form that I got, and if it's reasonable, I don't have a problem with it, but I prefer to get the form simplified. So in this case, you can combine what's circled in red there to the lower form, which immediately follows from the shifting theorem, which would say inverse Z transform this piece, and then I replace n by n minus 1, and that's exactly what you have here. I mean, if you had your choice, which of these two would you use? The delay theorem, or would you use the line division? And yeah, you'd always use the delay theorem. So multiplying by an exponential would be an example of multiplying in the time domain and seeing some sort of morphing example in the frequency or in the Z domain. But here, in terms of the Z transform, what happens if you multiply by Z naught to the n, it ends up changing the argument of the Z transform. It becomes Z over Z naught, whatever that factor is. And the main thing that does, besides changing Z everywhere by putting in Z over Z naught, is it takes the region of convergence and effectively multiplies it times the magnitude of Z naught. So the region of convergence will have its inner and outer radii changed by that Z naught. There's also a differentiation theorem, which says if you differentiate in the Z domain and multiply by minus Z, you get n times x of n. And that, the proof of that is down below here, just going back to the definition. So I'm going to use that theorem to just show you that what is the Z transform of n times a to the n u of n. If I look at taking the derivative of a to the n u of n, I'm going to get a times z to the minus 1 coming out. This is from the quotient formula for derivatives. And then you can establish that again, by the use of the theorem, that on the time domain side or sequence domain side, it's going to be A times A to the NU of N. And what's gone on here is that this is included in that, but then when it works itself in for this particular case, again from the quotient formula, that this minus C gets absorbed after this derivative is done with this. So what I'm going to do with this is I'm going to try to do something. There it goes. Okay. I'm just wanting to do something on my scratch paper over here. If it's going to paste, which it's not. Oh, come on. I practiced at this with this tool, and it worked for me last night, but it's not working for me right now. I was just going to make life easier, but instead I'll go back and just copy it by hand. So what I wanted to just show is that this is related to the result we had before. This is using the differentiation theorem, but what I'm after is n a to the nu of n, a z to the minus 1. Okay. That's what we just showed over here. Let's make sure I copied that right. Okay, I copied it right, and it's and it's causal, so I can do that. Earlier today, though, when we were trying to get the inverse Z transform of that, what did we have to do? I just gave you the answer, but now that we have this theorem, which is the blue result up here for the repeated pole, what we really have to do is we just have to make that go away so that it looks like what I have in red. So if I take that a z to the minus 1 that's on the top and use time shift and linearity, if I'm going to remove that down here in the red, effectively over here on the time domain side, I'm going to have to do what? I have to bring the A underneath because I don't want it to appear on the right side. And then the z to the minus 1, if that shows up in the time domain side, what does, on the z domain side, what is going to be going on over here? N is going to go to what? Is it minus 1 or plus 1? Because I'm undoing what was done, right? So let's just carry that out then. Every place I have an n, it's going to be an n plus 1. I have a to the n then I have the 1 over a out in front. And now because we've backed up one sample to the left, you're thinking, that seems kind of funky. But what's going on at n is equal to minus 1? At n is equal to minus 1, if I replace n with minus 1, I'm going to get 0. So having a non-zero value at n is equal to minus 1 in this sequence is moot because it's annihilated by the 0. So in reality, it just says that I can go ahead and, well, just say that this is now I'm going to divide through one of that a out in front, so it's just a to the n. Just that, because of the fact that the n plus 1 part of the solution doesn't exist, because it goes away. These little nuances can show up at this. The idea here was that this is the transform pair. That was utilized in working that problem earlier.
Can you explain one more time why the u to the n plus 1 just goes to u to the n?
It's because, get the right color here. At when n is equal to minus 1, which is when that step first turns on, at n is equal to minus 1, the n plus 1 is 0. So that term is not needed. It doesn't represent anything. So that's how that transform pair got derived, though, or at least this is a way of getting that transform pair through the differentiation theorem and then through linearity and time shifting. All three of those properties were utilized in getting this. Linearity said the A could move across to the other side, right? And the time shift theorem said that I could undo the z to the minus 1 by backing the sequence up one sample to the left. Just little fidgety things that happen when you're doing stuff like this. Conjugation, time reversal, probably this one is of interest in certain circumstances where you want to consider what happens when a sequence runs the opposite direction. So here, if the sequence is running backwards, because n has been replaced by minus n, then in the z domain, z is replaced by 1 over z, and the region of convergence is 1 over the region of convergence of the on-flipped signal. And the 1 over is slang. That's just as saying that the region of convergence goes between r sub r and r sub l, the inner and outer radii, that the 1 over that is this thing I talked about last week, the turning a sock inside out, where now the inner radius is 1 over the outer radius from before, and the outer radius is 1 over the inner radius. So it just morphs it in that fashion. There will be an example of this that's going to show up in Chapter 4 when we're proving something with random processes. So that's about the only time that I think that this gets used, but it is useful. And this, a simple example is if we have u of minus n, we know that u of n is 1 over 1 minus e to the minus 1. Apply the theorem, we'll get 1 over 1 minus z. Put that back in terms of negative powers of z. We'll see that we've shifted, we delayed by 1 sample, and then we have a minus sign on there now as a result of this operation. And the region of convergence is the interior as opposed to the exterior. This is a special case, kind of a theorem, but it's insightful. And eventually in Chapter 5 we'll be talking about minimum phase systems and some other interesting things. It might be helpful there too. Okay, this theorem is extremely important. It just says if we convolve two sequences, we multiply their Z transforms, and the proof of that is written out here. Again, just like before, the region of convergence, just like when we add two Z transforms, when we multiply them together, we have to consider the fact that we're going to be intersecting the region of convergence, or it may be larger if there's a pole zero cancellation going on here. And this is a throwback to Chapter 2 when we convolved a step with an a to the n u of n. We can just do that in the Z domain now. We have this as our y of z. This is like a system example, right? And it's probably better to think of that not as a separate signal, but just as the Z transform of the impulse response of a system. But that's where this shows up in practice, where we have one signal passing through a system, and we look at it as a convolution in the sequence domain, and then its multiplication, and the Z transforms, and then inverse Z transform it. So we have two simple roots, and one at 1 and the other one at A. So we take the maximum of those two, and assuming that our system is stable and causal, or the A, 1 over 1 minus A, Z to the minus 1 is like our system, which would be like an RC low-pass filter, and we're driving it with a step function. So the 1 would be the region of convergence in the output, since that's the maximum pole radius. And then we just write that all out, and we get this term-by-term inversion, and then put it together. This is the geometric series answer that we saw before. It rises up instantly, and then it decays off as time goes on, because the system is stable. So this would be like the step response of an RC low-pass filter, which, if you're tired of me saying that, I'll just remind you again, it's because I think so clearly to me that I learned about analog systems and I learned about RC low-pass filters, so far back in time, and it's just a foundational concept. Take a computer scientist that would come in and take this class or learn about discrete time signals and systems. They don't have that, right? I don't know, I'm biased, but I think electrical engineers or computer engineers are very powerful on the scene for solving problems, because I deal with this all the time. My implementer of my code in Python for this system I'm working on is an electrical engineer, and he knows VHDL, but he probably doesn't practice as much of his circuit theory that he learned way, way, way back when. And computer engineers tend to be more like that too, but they did see it once. If it was a person that never saw it because they were in computer science, then it's a lot harder. Think about that, because you deal with that through your entire career. We're all team players, though, so we all bring pros and cons into, I shouldn't say pros and cons, we all bring in different strengths, and when we combine those together, we have a powerful thing. We don't have something that's weaker. It's the positive things combine, the negative things no longer hinder us in general, and we just have to help each other out. So I rely on the computer science people to help me out with Git and other such things that maybe confuse me in that area, or software practices. We'll see this at some point too, but the initial value theorem, I see an application. The initial value theorem just says that we can get x of 0 from x of z by letting z go to infinity. And there's a final value theorem too, but this is just demonstrated in here, the initial value theorem. Okay, contour integration, all the complex variable background, we're going to skip over. So we're going to roll on down a long ways. And we're going to end up at the time-shifting property, but it's going to be under the unilateral Z-transform. I'm going to try to make this really short too, since I'd like to do something with Chapter 4. But the one-sided Z-transform, remember, starts at n is equal to 0, and it lives, I don't know. Okay, the new projector did not help. This is bad news. Meanwhile, we're restarting. Dr. Tromboli and I exchanged information this morning. He's never had a problem. I've always had this problem. I swapped out a projector. So what's wrong with me? Maybe that's what the conclusion is going to be. Really? Yeah. I don't know. I mean, it took weeks for computing services at Dr. Tromboli's hinting to say, just swap in a spare, because that's what electrical engineers do all the time, right? We have a spare, we put it in, and we go figure out if that solves the problem. We know there's something wrong with our unit, but Dr. Tromboli and I use the exact same computer. I just don't think there's anything that I'm doing that's wrong. And if you said Dr. Song did it, she had a different computer probably than I do, right?
Yeah, she did. She uses her laptop.
Yeah, this is a department-issued laptop, but when we bought laptops last, Dr. Platt, Dr. Tromboli, and I all bought the same laptop, and a lot of other faculty bought something else, just because we have this great freedom here. We can do what we want to do. I mean, we're allocated a certain amount of money, and when we're given that amount of money, we can buy what we think we want to have. So at any rate, we're back up and running. The unilateral case, though, lives a life of ignorance in the sense that if the sequence has values prior to n is equal to 0, the unilateral Z-transform does not have knowledge of them. But it still exists. Still use geometric series to solve the transforms and use lookup tables via partial fraction expansion. So what is special and what comes on the scene with the unilateral Z-transform is the ability to solve boundary value problems where we have a system that has initial conditions in it and we're starting it at n is equal to 0. And this is the parallel to the circuits problem, where you had the Laplace transform and you wanted to solve electronic circuit where you might have some initial voltage on a capacitor or current through an inductor. Standard classical problem that I remember getting beat into my head over and over again. That's what we want to do this, because in electronics or circuits we have those scenarios going on. So one of the interesting things is, what is the difference? As long as n is greater than 0, or if we're considering the Z-transform of, say, a signal that's been shifted to the right, there's no difference. If it's shifted to the left, we're going to have potentially a radically different solution. We're going to have 0 versus something. So to get into how to do this, I'm just going to say we have to establish a time delay theorem with a one-sided transform and figure out how to work that in. And because I'm not going to give you any homework problems on this, and it's not going to be on the exam, I'm going to cut to the chase. I'm going to get to the final summary of the results. The details are all in here based on how the one-sided Z-transform relates to the two-sided Z transform. But here's the summary of the results. For solving causal LCCDEs, which means things that start at n is equal to 0, we have this is our standard difference equation at the top, which we had back in Chapter 2. So we have this, but then what we have is we have initial conditions. We have some initial states in this system, which we use when we solve it. So we're going to have past values of the output, and we can have past values of the input, so to speak. It's generally harder to think about past values of the input because the input doesn't really exist. We're assuming the input is turned on and n is equal to 0. But certainly the states of the system will mean that there's some history of what's inside the system that controls how it starts up. So we take the unilateral Z transform on both sides of the difference equation, and when we do that, thing that's going to happen from studying the delay theorem is when this side gets transformed, we get two terms now. We get a term that looks just like the two-sided Z transform. Then we get this term here, which is related solely to the initial conditions. So it's a term that only exists if we have non-zero initial conditions, because you can see this y of m, as m runs from minus k up to minus 1, that is going to contain those initial conditions. And then it's controlled furthermore by this n out here. So that's just the initial conditions term. And then on the right-hand side, we have the same idea from Z transforming this side. So I have to draw my arrow like that, have it come down. We have the standard transform result, same as the two-sided transform, and then we get, again, this related to initial conditions on the input. So if we're in a at-rest system, which we are when we do the impulse response of a system from its difference equation, these terms never exist because, remember, in an impulse response, system is always at rest. If we're in a system, though, where we're going to have initial conditions, or the example I'm going to show in the notebook here where we want to process multiple vectors and carry forward states that were left after the first vector was processed, then we will have this to deal with. So when you end up solving for y of z, the standard result holds for zero initial conditions. We get this, x of z times the transfer function ratio, numerator and denominator, for h of z. And then, assuming that there are initial conditions present from this term here, that will get modified by the poles in the system. And the initial conditions on the input will get modified by the poles in the systems. And those will be the zero input responses. So together, this would be what you would call zero input. So it has nothing to do with the driving function. It's just what were the states in the system when it started up, and they're going to, presumably, if the system is stable, the denominators there are poles inside the unit circle, and as time marches on, it'll decay off to zero. So I did do a simple example here and followed through for a first-order system, and this is like the very, very first difference equation we solved. You end up with this is the term that comes out of this, and that comes about from this. That's the only term that survives out of this red box term. In other words, it's one of these guys has a component, and that's a times c, 1 minus a z to the minus 1. That's the only thing that comes out, and then that will be the zero input response. and it rolls on, and Python manages that beautifully. So I'm going to, rather than talk about it from here, I'm now going to switch to the notebook, because the notebook actually tells you how the functions work, which is very cool. Python has functions that handle this. MATLAB has something similar. It's another function that's added beyond lfilter. Lfilter is what we use right now, and lfilter can handle initial conditions. But if we have to set the initial condition state array for lfilter, we have to use this new function called lfilter IC, or lfilt IC. So its sole purpose in life is to establish initial conditions that can be loaded into lfilter that are other than 0, and you get to create those using the same B&A vectors you would use in lfilter, and then you have this third entry is the initial states on Y, which you see right down here. I can't mark on this, but I guess I can't highlight it either. At any rate, that's that part, and then if desired, because it's optional in here, x equals none means you don't have to supply anything, but if you decide to have x equals something, you could set initial values inside of this. So that's available. So in this example, what I've done is I've just said here's our h of z, so we know that b is equal to 1 and a is equal to an array 1 minus 1 comma minus 0.8, and then I just know that the initial state is going to be minus 1 times 0.8, and that will then allow this simulation to start at n is equal to 0, and I'm going to fire the input on it, n is equal to 5. So when I run this, I'm going to see that the input turned on here at 5, but starting back at 0, this was this initial state that was starting at minus 0.8 and is just starting to decay towards 0. And now this guy comes on with it, and this whole thing just marches on down in time, and this eventually decays off to 0 and leaves the scene. So this is my big exciting thing to do before I move off of this, and that is initial conditions can provide continuity between data frames. So we can process a long frame, and then we have to come back later and process the same frame, picking up the next time instant. We want to maintain continuity. So what we would do in this case is, for this filter operation, we're going to use the lfilt IC with B and A, and we're going to just say start with a 0 initial condition and create our array ZI for 0 initial condition. And then when we go ahead and filter, we're going to include the initial condition, preload that in, and we're going to pull out a second argument out of lfilter called ZI. So 1 is the input, and then this is the return state for the next time we might call the function. So it's the same ZI, it's just been updated, represents at the end state. And then the next time we filter, we pass it back in again, and then we take it back out again. So here what I've done is I've created an array from 0 to 100 of a cosine, and I'm breaking it up into two 50-point sequences. We're going to do the first 50 points here, and then we're going to do from 50 out to the end in this second line and store those in the same array, but moved out. So when I run this, and I have the initial conditions properly managed, what did I do? Oh, I didn't run this. Okay, got to run that. Come down here, and I look at this, and I say, it looks like I'm filtering a signal, and right here at 50, I just see it smooth as smooth can be. It's just, it handed the first 50-point array and started filling from the second 50-point array just fine. So it's doing the right job. If I ignore the initial conditions, never use them down here, and try to play the same game, we're going to see that happen. It's going to reset back to 0, not realizing that this was streaming along. So this, to me, as a signal processing person, not as much as a control systems person, this is very valuable. And you will use this when you're doing real-time filtering in Jupyter Notebook using Pi Audio. In the lab, same thing is done. The states are held in C arrays, but it's the same idea. We're holding state, and then we're going to pick up again. And that's for efficiency that you would run things in segments like that. Is that good? I mean, you're going to come back and see this. What's in the rest of this notebook, which I'm not going to take the time to go through, I have you look at, is I've got some other examples in here for homework problem checks. So I've got 3.3c. I guess that's the only one in here, but they're there. So just give you ideas of how I want to push you into doing that. Okay, so now a brief introduction to amazing chapter 4. Sampling of continuous time signals is what the author of the textbook calls it, but I've included other things that we haven't had a chance to talk about into here from chapters 2 and 3. So we will be going through sampling theory, standard stuff, getting the notation established. We will then look at discrete time processing of continuous time signals. Then we'll enter a newer topic, namely rate changing. And we'll look at rate changing up and rate changing down, and then multi-rate, rate changing. We'll eventually go off and look at something called polyphase decomposition, which is very popular in practice. All the systems that I work on these days in my work are all multi-rate, and simulation projects can be multi-rate, of course, too. Along the way, we'll go into the bandpass sampling theorem, and that's a nice example. It's embedded early. And then the tail end of this chapter gets into a new topic, discrete time random signals, quick review of probability, random variables, and then jumping into this new topic, random processes, which is going to be useful later on. It just so happens the book started running this in the background. There were a few random process examples in chapter 2. There might be some in chapter 3, but then there's certainly some in chapter 4, 5, and 6, and so on. So I just put off getting started on it until now. And then the last part is just looking at some practical matters of signal processing of analog signals, having to include anti-aliasing filters, looking at quantization effects, and then a fun practical topic that is addressed in a couple of the homework problems of the book, I'm not sure if I've assigned those, is oversampling in noise shaping. And this gets into a topic called sigma delta or delta sigma. Have any of you heard of sigma delta converters? So we'll discuss the magic of sigma delta converters. Very powerful in our society, I should say. I mean, every time you listen to anything through your earbuds or anything, it's all based on sigma deltas, which are very powerful signal processing. It's multi-rate processing. It's DSP side of the equation saying you analog guys need some help getting your A to Ds and D to As to work up to what we'd like to have you do. We're going to grab some things from you, and we're going to make your life easier, put more burden in the DSP domain. Doesn't that sound, maybe that sounds political in some way. We're not trusting you. We can do it better. But it's just, again, saying that DSP has become more powerful because of the processors, and the sigma delta still puts a burden on the analog developers to develop something very powerful on their side. But we'll learn about that. It's just sort of for fun to learn about it. I think it's kind of exciting, though, in motivating that whole topic. So where do we start? Chapter starts very simply at just saying this is the chain, and if I blow this up enough, you can see better what we're talking about. A signal might come in band limited, so we know we can't sample at greater than twice the highest frequency of a square wave because it goes on and on and on, so we're going to band limit it. When we band limit that with the anti-aliasing filter, we introduce some ringing. When we get ready to digitize it, we end up turning this infinite precision band-limited square wave into quantized levels, and I just sort of drew them big enough to see. They're generally so small. The 16-bit converter, there's 2 to the 16th minus 1 quantization level, so you don't see them in a picture, but they are there. So the sample and hold and A to D converter kind of work together, convert those samples into digital words that say would be 16 bits long, assigned 16-bit integer, which Python supports, C and C++, all those languages support. The DSP processor works on the finite precision math, produces an output samples, say signed integers, and then gets ready to send it out to the D to A converter. Again, I'm showing some quantization that's present in here, and here I'm sort of saying that these harmonics got reduced and we pretty much just have the fundamentals. So that's why you're just seeing a sinusoid there. Then the reconstruction filter takes it back out to the analog domain. And the sigma deltas work in concert with that, but in the beginning and in the really high frequency systems, they use more analog filters still for reconstruction. So we'll also talk about that. Any questions on that? I think I'm just going to stop right there. Is this sounding exciting? I mean, to me, this is where it starts to get more practical. I can now bring everything else in. So we'll start with periodic sampling and something that we'll need. We're going to need some continuous time Fourier transform, so I have a quick little review of that. I didn't get a chance to talk about any homework problems specifically, but I think I hinted at things you can do. Message me if you think you need to know more. I'm going to see what's going on with the student number 5, who I'm guessing is messaged me twice. But I should see him in lab.